let's continue. Now we have discrete time LTI system. Instead of Laplace transform, we use Z transform. The inverse Z transform is not shown here because nobody use this inverse transform because it is very complicated. The forward is very easy to be performed on a discrete time signal. What is the relation between Z transform and Laplace transform? We have two formulas. Our complex Z variable is e to the power of the Laplace operator times the sampling interval. There are many important properties of Z transform, but we are going to use only two. The first one is that this transform is linear, and the second one is the time shifting property. If we have a signal x of n delayed by k samples, it is equivalent in Z domain to find the transform of the original signal without delay and multiply by Z to the minus k. K is delay. And here we have transfer function y of z over x of z, and y and x of z are the z transforms of x of n and y of n. Again, for a discrete time system, we have a transfer function and we have the impulse response. They are related. Just by applying the Z transform on the impulse response, we will get the transfer function. In Z transform, in our discrete time systems, we have pole zero plot, but this pole zero plot is the following. Here is the real part, here is the imaginary part of Z. This is discrete time, this is continuous time. For continuous time analysis, we have sigma j omega, and this axis j omega, when we move from continuous time to digital time domain, we, how to say in English, we bend this axis and it becomes circle, unit circle. Our zeros and a pole, or 12 poles. Now, the important here is here we have zero frequency. When we move counter clockwise direction, here is the Nyquist frequency, Fs over 2. And if we continue to move, here we are at Fs, at the sampling frequency. In a continuous time system, we work with frequency from 0 up to infinity. For discrete time system, we work with frequency with 0 up to sampling frequency. Now, because here our stable system has poles on the left side, can you guess in digital version where the poles have to be to have a stable system? Inside the unit. This is a stable system. This is not a stable. Now, let's start the last topic for today, digital filters and multi-rate signal processing. If you have any questions, last topic is 1D DSP. We will talk about digital processing of one-dimensional signals. They are in most cases function of time, discrete time. We will talk about digital filters and basics of multi-rate digital signal processing, if we have enough time. Here is the idea of digital signal processing. We take real world signals, process them with in digital form, and we can restore them back in continuous version. We have to, if we have to make digital signal processing, it is enough to work with very elementary mathematical operations, multiplication, subtraction, and divisions. Nothing more complicated. But we have to make and some logical operations, such shifting, but they are not hard to be implemented. Our digital filters, they change the spectrum of the sampled or digital signal, but the algorithm can be described in time domain. Mostly they are software realizations. Sometimes can be seen hardware versions. For example, when we implement them in programmable logic devices, FPGA or CPLD. Only two arithmetical operations, multiplications and addition. Sometimes in digital signal processor, they are referred as MAC. Multiplication and accumulation. DSP are very optimized for such tasks. Two structures, finite impulse response FIR and infinite impulse response IIR. The first one is without feedback, the second one is feedback. Our algorithms, the first and the second, contain constant coefficients, so we can think about our filters as digital LTI. Sometimes these coefficients are not constant, so such systems are linear but not time invariant. We have the simplest case, constant coefficients. And what is the advantage of using digital filters instead of analog? There are many. Accurate processing. We don't have coils, capacitors, resistors with their temperature and time drift. Everything is mathematical operations which are exact, and we don't have we have very stable processing. Some filter characteristic can be done in analog form, in analog domain. We can make our digital filters just in software, and we can change the coefficients. So by changing the filters coefficients, we can readjust the filter behavior very easily and very quickly. If we have an analog circuit with analog elements, if we want to make a high pass filter from low pass, we have to change the interconnections, which is not very convenient. In our software realizations of digital filter, it is quite easy. When we have to filter very low frequency, in analog version we will have large coils and capacitors, which can increase the cost of the device. In digital form, it doesn't matter, only the coefficients are different. Not every analog filter can be replaced by digital, because sometimes we have to process very fast signals. We don't have such a powerful processor or fast analog to digital converters. Sometimes the analog filter cannot be replaced at all. We have the following situation. We have our analog to digital converter. Here we have anti-aliasing low pass filter. This filter cannot be digital because it is in front of the analog to digital converter. If we omit this, we will have aliasing, which is not desirable. It cannot be replaced, only analog version. The first structure.
Is there something like a hybrid? So not purely hardware, not purely software?
A very, very good question. May I answer a little bit later? Okay. This is our first very simple structure. FIR, finite impulse response. Here is our input signal, here is output signal. We have summation, we have multiplication by coefficients, and we have a delay line. Here is the current sample, here is the previous sample, here is the previous, and so on. Very, very easy to be written in C language or. Here is the delay line. It's not included memory. Here is our input signal. We have a new sample. We write in this cell. We throw the last and make the following: a cube. let's say here is x of n, here is x of n minus 1, and so on. We multiply by coefficients and we make addition, and here is the output. Here is the input, here is the output. Just a different point of view. So, the answer to your question. This filter have a unique property of linear phase response. Linear phase response is sometimes very desirable property because we don't have phase distortion. We want, do you agree that every filter delays the output signal in respect to the input? Of course. But our input signal has a lot of spectral components. We want each harmonic, each spectral component to be delayed by some identical amount of delay, because we want to sum the output them with right phase. We want same delay, but if to achieve this, we want linear phase response, which is can be achieved only by FIR, not in analog domain. Some they try to make such thing in analog domain. The addition is easy. You can use op-amp or resistor network to some analog signals or voltages. But what about multiplication? This can be done by operational amplifier. It just amplifies the signal. No problem up to here. How to realize the delays in analog domain? It's not impossible, it is possible, but you can't match them exactly the same delay between each tap. It's not possible in analog domain. Because in digital domain, we actually don't have a delay, we have a register. And by shifting, we can make this delay. Why? But in analog domain, how can we delay a signal?
Making longer path propagates.
It is very different to be made, and it's very different to be matched exactly. And a group of people have tried to make such thing, and the result was disaster. So maybe it's not possible. Answer to your question. The difference equation. What is the input signal? Obviously, the output signal, is the input signal x of n times b of b0 plus x of n minus 1 times b1 plus x of n minus 2 plus b2 and so on. We have our difference equation. Very simple. In analog domain, this is not a difference equation, this is differential equation. Here the things are much simpler. This is our algorithm in time domain, very elementary. And capital N is the filter order. Now, because this is a LTI system, we want to find the impulse response of such filter. We can apply delta as input, and the output will be our impulse response. But it's very obvious if we apply delta on the input, it will multiply by this coefficient, but other coefficients, the delay line in the delay line will be multiplied by 0 because we have delta is 1 only here, but is 0 outside at any time different from 0. So if you apply this one will be multiplied by first coefficient, the rest of coefficients will be multiplied by 0. So in the next sample interval, this delta will move here. And now at the output, we will see the coefficient B1. At the next sampling interval, we will see the next coefficient B2. So very obviously, the impulse response is the same as filter's coefficients. So can we make coefficients to be infinite? No. So finite impulse response. Here, if we substitute in the above equation B with the impulse response, we get something very familiar. This is our convolution in digital form. And we want a stable system. Stability means that our impulse response should be 0 at n when n tends to infinity. But because this impulse response is not infinite, this is always true. So the second very unique property of FIR structures is that they are always stable. We don't have to investigate their stability. Very, very good property. Linear phase and stability, unconditional stability. We can apply Z transform on this difference equation, and we can find the transfer function. Here is the transfer function. We apply Z transform on both sides. We take into account this property of the Z transform, and our transfer function is simple sum of our coefficients times to Z to the minus 1, minus 2, and so on. This transfer function is composed only by zeros. We don't have any poles here. So actually, we can write Z to the minus k as 1 of Z to the k. K is an integer. So what value of Z will make h of Z to become infinity? Obviously 0. So our poles are always at the origin. But since they are at the origin, they are in the circle. So such systems are always stable. We can find the frequency response because this system is a filter. We want the frequency response. If we substitute Z with e to the power of j omega ts, and we consider the relation between Fourier and Laplace, instead of z of or instead of h of z, we can get the frequency response, which is a complex function, but one interesting thing. How do you think? Is it periodic or not? We have complex and exponential.
Yeah.
Periodic. The signal is digital, discrete in time domain, periodic in frequency domain. One more proof. It's periodic. We can find the magnitude and phase response. The working range for digital filter is always from 0 to the Nyquist rate, from here to here. But for analog filters, it is from 0 to infinity. That is the main difference. We mentioned about linear phase response. Now we can define the following thing. We call it group delay response. We want this group delay response to be constant for every frequency. Why? Because the group delay response is actually the first derivative of the phase response. We want a constant derivative. So, to achieve constant group response, our phase response should be linear. The first derivative of linear function is a constant. This can be achieved very easy if we make something like this. If the impulse response or coefficients have a symmetry or anti-symmetry. Symmetry means the first coefficient is equal to the last, second is equal to the next, how is in English?
First to last.
Okay, and so on. We can have an anti-symmetry. The first coefficient is the minus last, and so odd and even relation. If we have such dependency, symmetry or anti-symmetry, we have always linear phase response and constant group delay. Every filter introduces a delay. For such structures, if we have constant group delay, this delay is equal to the filter order divided by 2. If we have a filter with, let's say, a 4 to 10, it will delay the output signal in respect to the input to the 5 samples. Very good thing, because we can predict the delay. Some elementary filters. This is a delay filter. It has just one unit coefficient of k. Such filter doesn't change the magnitude response, but introduces a delay. We will see this in the simulation. In simulations. Now, the next type of filter, is averaging filter. We can achieve average of our digital signal if our filter has equal coefficients. This is moving our average. So we know the average is low pass filtering. We have low pass filter here. This is the magnitude response. Not the best one, but still low pass. Another filter, a fire comb filter, example with two tabs. Such filter has a magnitude response shown here. It attenuates two frequencies. The first one is here, the second one is here. And the next type is the structure with feedback called infinite impulse response, or IIR. The idea here is the output signal depends not only by the input and its history, it depends on previous values of the output. We have input signal here and delay line. We have output signal and delay line. We involve feedback. And what is the idea of such feedback? We can make a desirable magnitude response with very few taps when we use this feedback. For these structures, if I need 100 taps to achieve almost the same, I will need here, let's say, 10. This is good thing because we save memory, we perform much less arithmetical operations, and the ability to work in real time is always satisfied. Now, another structure, they are identical, but the idea is we can think about two filters. The first one is up to here, and the second one is from here up to here. So they are connected, they're in cascade. First one and the second one. Because we have LTI, I can change the positions and the transfer function will be the same. If I swap right and left part, I can merge the delays and we can save memory. First is direct for 1, the second is direct for 2 of IIR. The difference equation, it accounts not only the input signal, but previous values of the output signal. Here is the feedback. The order is the maximum of N and M. And in such filters, we have transfer function, which is composed not only by zeros like Fi. Here we have zeros and poles. That's why we can achieve a desirable magnitude response with very few taps, because we have now both zeros and poles. How do you think? Are they always stable, such filters? No. We have poles.
Could be anywhere.
Can be anywhere. So, if we want a stable filter, we should investigate the pole zero plot and to see if the poles are inside the unit. We pay for such small taps with possible instability, and something important, these filters do not have linear phase response. We have phase distortion in IIR structures. the impulse response for these methods is not, can be directly associated with the coefficients. So, but we can find them using the inverse Z transform. This is always true for every discrete time system, linear LTI system. And we can substitute Z with e to the j omega ts, and we can find the frequency response. Here we have numerator and denominator. We can find the magnitude response and we can find the phase response. Very clear, I think. And we can achieve a desired magnitude response with much less number of taps than FIR structure. But here we have nonlinear phase response. That is the problem. Sometimes it is not very important, but sometimes it is very, very desirable property. Here is the, we can compare FIR and IR structures. FIR is simple, linear phase response, always stable, and can tolerate arithmetic overflows, whereas IR structures may have problems because of the feedback. If we have arithmetic overflow, it will continue because of the feedback. FIR structures are with much more taps. They introduce significant delay in applications such as VoIP and VoIP. This could be a problem, but sometimes it is not important. And IR structures require less amount of memory. Let's show some characteristic of some elementary FIR. Simple averaging, excuse me, averaging of two samples, low pass filter, magnitude response, linear phase response, group delay response, and pole zero plot. Can we associate this zero with this magnitude response? Of course, our subclick rate is 1 kHz. Here is the half, here is the Nyquist frequency. And this zero corresponds to this here. We can make average of, let's say, 5. Of course, more zeros and better attenuation. We have frequencies that can be attenuated very well. And how do you think the phase is the phase response linear? It is here. You can see you have discontinuities here and here, but it is not important because here the magnitude response is 0. For us, it is important to the phase response to be linear here, here, and here, and the slope is the same. We do not expect any phase distortion. maybe it is better idea to switch to the next demo. We can see how can we attenuate mains power interference in electrocardiogram. FIR structure. Here is our mains interference. You can see the result here. Almost perfect, but we have delay, significant delay. This is the original, this is the filter. Here is the signal with interference. Now, this FIR structure is with is of order 128. We can try to achieve something similar using IIR structure, only of order of 8. Pole 0 plot, the poles are here, and you can see we have an insignificant delay, but you can see here the result of phase distortion. No delay, but we have phase distortions because because we don't have a linear phase response anymore. This is the group delay, but the phase response is here, not linear. How to design such FIR filters? We choose a magnitude response and we want to find the impulse response. We can apply inverse Fourier transform to find the impulse response, and the impulse response is our coefficients. But the idea is, if we have an ideal filter with Bricol response, frequency response, if I make inverse Fourier in time domain, I will have the impulse response, but it will be sinc. How long? Infinity. I cannot make infinite number of coefficients. We can truncate up to here. Do you agree? Now, we will not have an ideal rectangle anymore. But this impulse response corresponds to non-causal system because it is non-zero at t less than 0. So we have to move it. And now we have causal filter. Very simple approach. This type of truncation with rectangular window doesn't give very good results because we have ripples here. We want something different to window the impulse response, something like this, to minimize the effects of such discontinuities here. Many types of windows, Hamming, Blackman, you have the formula here. A short comparison of the windows and the results in frequency domain. Here is the rectangular windows. As you can see, the worst case. The things are much better here using Hamming and Blackman. A few words about, and this will be, we don't have time, we have only 3 minutes, about the design of infinite impulse response. The idea is to make an analog filter and to transfer it in digital domain. We can try to substitute the Laplace transform with the Laplace variable with Z variable, but we won't get a rational function. So this is not our approach, but we can use the following series, S and zeta, which is z minus 1 over z plus 1. If we omit these members, these terms, we can use this relation, very simple, Laplace and z operators. But we can make an analog filter using Laplace transform and transfer it into the digital version. But we don't have linear dependency between analog and digital frequency, because the analog filter works with frequency from 0 to infinity, and the digital filters work with frequency from 0 to the Nyquist rate. And if we try to make an analog filter, we have to consider this non-linearity, digital frequency and analog frequency. We have the following relation, analog frequency and digital. When we try to make an analog filter, we can pre-calculate the cutoff frequency according to this. After that, we can synthesize analog filter, and after that we can transfer it into the digital domain. Here is a short example. We want to make a filter, digital filter, with cutoff frequency of 100 Hz. The sampling frequency is 1000. Now, we want to use Butterworth approximation for the analog prototype. Here is the approximation. Now, we have to pre-calculate the cutoff frequency. Our cutoff frequency is 2 by P by Fc, which is 628. If it is substituted in this formula, we now see that our analog filter will have a cutoff frequency which is quite different. If this frequency was very low here in the linear region, the things will be okay, but now our filter is uses Butterworth approximation, so we substitute 650 in the cutoff frequency, and we substitute S with Z with some very elementary rearrangements. We get this, and by inspection we see this is B0, this is B1, this is A1. And our digital filter is Okay. We don't have time for the rest, but I will give you all slides as soon as correct my mistakes in them. Thank you. If you have any questions, please. We are exactly in time. The rest is very few.